Hi everyone, and this is the makeup lesson on the different types of chemical bonding and the properties that are associated with each of those types of bondings. So we started today by completing a Do Now in today's Schoology folder. If you missed class today, please make sure you're going ahead and submitting that. Our learning target for today was, I can predict the properties of a substance based on its chemical formula and model of bonding. So we started by recalling from yesterday what the definition of a chemical bond was. And we said that it was a lasting attraction between atoms. And that this lasting attraction had to enable a chemical compound to be formed. We haven't learned yet in chemistry about types of attractions that do not enable the formation of a compound, but we'll get to those later in the year. The forces of attraction between atoms in chemical bonding need to be so strong that the atoms are physically held together. We then took a look at this example, which is an example of something that we call covalent bonding. Hopefully everyone has heard of covalent bonding, even if they don't remember what it is from 8th grade science or biology last year. But this is a type of bonding in which electrons are shared between atoms. This is in contrast to the type of bonding that we first started learning about in chapter 4, which is ionic bonding, in which atoms transfer electrons to one another. The forces of attraction within chemical bonding are very similar to the forces of attraction within an atom itself. So here we have electrostatic attractions between the negatively charged electrons and positively charged protons, just like our atoms feel internally. The difference is, now that this pair of electrons has been shared between two atoms, each electron feels a force of attraction between both positively charged nuclei on each of the atoms. And so you can imagine that it's kind of being pulled in both directions, each of these electrons. And these pulls are what allow the atoms to be tethered together. The 4 different types of bonding that we first learned about yesterday and will continue learning about in more detail today are metallic bonding, network covalent bonding, molecular covalent bonding, and ionic bonding. As we go through these slides, we're going to see each of these models for each of the different types of bonding. And so I just want to make sure everyone knows what the different parts of these models are representing. So the red spheres on each of these models represent the nuclei and core electrons of atoms that are involved in this bonding network. And the blue areas represent the distribution of valence electrons. So let's zoom in just for a quick second on ionic bonding, which again we talked about extensively in chapter 4. You'll notice that only half of the atoms in an ionic bonding network contain these blue areas of valence electrons. And this is because, as we learned about in chapter 4, in ionic bonding, metal cations have transferred electrons to non-metal anions. So our negatively charged anions are these atoms here with the blue halos that have accepted valence electrons. And our positively charged cations are these plain red spheres that have lost all of their valence electrons when they were transferred to the nonmetals. Okay. And as you can see in covalent bonding, like we looked at on the last slide, instead of being surrounding one atom or another, the valence electron distribution in covalent bonding is between atoms because these electrons are shared. So our first model is ionic bonding. Ionic bonds are soluble, meaning that they dissolve in water. They are also conductive of electricity when they are dissolved. Ionic bonds are typically found in solid compounds, and both metal and non-metal atoms need to be involved in ionic bonding, just like we saw in chapter 4. This is because metal atoms will give up their valence electrons to nonmetal atoms. One will become positively charged cations, and one becoming negatively charged anions. Next is our first type of covalent bonding. So all covalent bonding involves the sharing of electrons. But we have two different types, molecular and network. In molecular covalent bonds, we sometimes have instances of solubility, though this isn't really a determining factor in whether we're looking at molecular covalent bonds. We never have conductivity. Molecular covalent bonds can never conduct electricity. Molecular covalent bonds can be found in any state of matter, solids, liquids, or gases. And they involve non-metal atoms only. So if you see any sort of metal in a molecular or chemical formula, we're never going to be looking at an instance of molecular covalent bonding. Molecular covalent bonding is probably the type of bonding that you're most familiar with. Examples of substances that are bonded through molecular covalent bonding are H2O, water, and methane, CH4 gas. If we only see metal atoms in our compounds, it is likely going to be an instance of metallic bonding. Metallic bonding substances are not soluble in water, and this should make sense to us if we think about it. If I drop a penny or a nugget of gold or silver into a glass of water, it will not start to dissolve. They are conductive for electricity, so if I hooked up a piece of metal to a battery, I could power a light bulb, for example. And they are always going to be solid at room temperature. So in metallic bonding, we have an interesting model over here in which the valence electrons between metal atoms are free to move about the substance in what we call a sea of electrons. So if you can imagine the valence electrons from this atom up here, they can be released and they're almost slingshotted all around this different network of metal atoms. Okay? They are not tethered to any one atom in particular, and this makes the bonds amongst metal atoms in metallic bonding very strong. Finally, we have network covalent bonding, which is, again, another type of covalent bonding where we see the sharing of electrons. But in contrast to molecular covalent bonding, these bonds are much stronger because they're happening in all directions from a central atom. So let's say, for example, we're taking a look at this atom right here. This atom is going to be sharing electrons with 4 other atoms on all sides, as opposed to molecular covalent bonding in which valence electrons are shared usually with just one other atom. This means that the network covalent bonds are much stronger and harder to break apart. So they are not soluble. They are also not conductive, just like molecular covalent bonds. Because the bonds are so strong in network covalent bonding, network covalent bonds result in extremely hard solids. So 2 examples of network covalent bonds are silicon solid and carbon solid. Carbon solid is actually diamond, which is the hardest substance on Earth, and it's built of these really, really strong and tight network covalent bonds. Network covalent bonds also can never involve metal atoms. They are going to be made up entirely of either nonmetals or metalloids. So the reason that we're learning about all of these different types of bonding is, one, so that we can understand why the properties of different chemical substances are the way that they are in future units, and also so that we can be able to predict some of the properties and the types of bonding present in compounds when we see them. So we can predict the type of bonding present in 2 ways. One, we can either look at the chemical formulas for that compound and use the periodic table. And 2, we can use the properties of the compound. Using chemical formulas and the periodic table, we're going to be able to distinguish whether the elements involved in the molecules are metals, nonmetals, or metalloids. And based on the combination or types of elements present, we can make an educated guess about the type of bonding. So if I only see metal atoms, then I'm going to be looking at metallic bonding. If I see both metal and nonmetal atoms, then I'm going to be looking at ionic bonding. And if I have nonmetal atoms or metalloids, I'm going to be looking at covalent bonding. And remember that this can either be molecular or network. In order to distinguish between molecular and network, we can look at two things. One, we can look at the states of matter. So these have to be really hard solids. But molecular covalent bonding can have soft solids, liquids, or gases. I can also look as to whether there are metalloids present. Now, metalloids can be present in both types of covalent bonding, but network covalent bonding are more likely to have metalloids. So if I see a metalloid and I also know that it's a hard solid or a solid in general, I can make an educated guess that that's going to be a network covalent over a molecular covalent. Secondly, we can predict the type of bonding using the properties of a compound. So using information on whether a compound dissolves or its solubility, and whether it conducts electricity, whether it's conductive, and taking a look at the combination of these two properties, I can easily predict what type of bonding will be present. So if something does dissolve, it is soluble, and it does conduct electricity, I'm going to be looking at ionic bonding. If it dissolves but it does not conduct, I'm going to be looking at molecular covalent bonding. If it does not dissolve and does not conduct, I'm likely looking at network covalent bonding. And if it does not dissolve but it does conduct, then I'm going to be looking likely at metallic bonding. So we can use this flow chart to help us predict what type of bonding is relevant as well. We could also work backwards from this flow chart. So if I know that I have a molecular covalent compound, I could work backwards and say it's probably not going to be conductive and it is going to be soluble in water. We then did a few guided practice questions before working on our independent practice. So we looked at what type of bonding was represented in each of the following substances using the chemical formula to decide. So here we followed this flowchart, identified each element as metal, nonmetal, or metalloid to make a prediction. In water, I have all nonmetals. And I have a liquid state of matter. So I can most reasonably predict that water is going to be a molecular covalent. In PT, platinum solid, I just have a metal atom. So this is going to be metallic. This is probably the easiest one. In C, solid carbon, I only have a nonmetal. And I have a hard solid. So this is going to be a network. Oops, this is going to be a network covalent. Remember, solid carbon is diamond, which is the hardest substance on Earth. And then lastly, I have MgBr2. Mg is a metal. Br is a nonmetal. So with this combination, I can assume that I'm looking at an ionic compound, just like we looked at through all of chapter 4. We then did a little bit of guided practice using the flowchart of properties. So if I have a substance that both dissolves and conducts electricity when dissolved, I'm looking at an ionic compound. Methane, if it does not dissolve and does not conduct electricity, this is going to be a molecular covalent. And finally, if I'm looking at something that does not dissolve but does conduct electricity, I'm looking at a substance that is metallic in nature. Okay. And I could also double check my work for all of these by taking a look at the chemical formula. So NaCl, I have both a metal and a non-metal. Sodium is my metal, chlorine is my non-metal, so this checks out that this could be ionic. In methane, I have all non-metal. And I have a gas, not a super hard solid, so this checks out again that this is covalent because of the nonmetals and molecular covalent because it's a gaseous state of matter. And finally, all I have in copper is the element copper, which is a metal, and so that must be metallic bonding. We spent the rest of class working on our independent practice, which is uploaded for you on ClassKick. Thank you, and let me know if you have any questions.